We have already spoken in the previous lectures about different growth processes that happen in biology. For example, we have spoken about logistic growth, or even more simpler, we have also spoken about exponential growth. But today, we are going to peer a little bit deeper on these kind of growth processes, and we are going to start by a very simple example. Consider, for example, a Petri dish, right? And then imagine that we have inoculated this Petri dish with some bacterial strain on it. Well, these bacteria will start growing, they'll start utilizing the resources that exist right at the border of this patch of bacteria. And therefore, we can imagine that only those bacteria that are right sitting here at the border, if we consider this to be an amplification of this image, these are going to be the bacteria that are allowed to keep growing. Okay? So in this case, we can acquire data for this system by considering different measures. We can, for example, measure how many bacteria are at time t, and then wait a little bit longer and look at how many bacteria are at time t plus delta t. Okay? And with that kind of data, we can start looking at what type of growth does this system exhibit. So we are now interested in, for example, looking at what's the amount of biomass that this system has over time. So let's pick up this variable. We call it biomass. This is the total mass of all the bacteria that are sitting in this Petri dish. And because we are trying to understand its dynamical properties, what we need to look for is what's the rate of growth of this biomass. In other words, we want to know how this can relate to the biomass already existing in the system. And this we can call it, for example, the growth rate, or the effective growth rate of the biomass. Right, so with all what has been said so far, now we can proceed to try to imagine what kind of relation is going to be between these two variables here. So remember, first off, biomass, if we think of this as a circularly symmetric, and we can pretty much think of that as a circularly symmetric system that it grows radially, right? The total amount of biomass, it's proportional, it has to be proportional to the surface area, right, that this circle is expanding with. So therefore, there's going to be a proportionality of this type, right? Well, we can ignore, this would be directly the area of the circle, but we can just pretty much ignore pi so far. We're going to just use proportionality. On the other hand, given what we have already discussed, namely that the bacteria that are sitting right at the edge of the system are the only ones that are capable to replicate and therefore keep advancing, we can say that this variable here, if you want that the growth rate, it has to be proportional. Instead of to the surface, it has to be proportional to the diameter, right? Which in our case, if we consider our approximation, our circular approximation, this has to go as 2 times pi times the radius. Now, these are going to give us a very simple relation, because, for example, if we look at here, this means that basically the radius is proportional to the total biomass to the power of 1/2, or in other words, the square root of the biomass, right? And this is a very simple relation that we can get here. Therefore, from this relation over here, we simply get that the rate of growth of the biomass has to be proportional. If you see there's an R here, well, immediately we can see that this has to be proportional to the square root of B. And now we have our the ordinary differential equation, and we are all about ordinary differential equations. Let us write down again this equation here, only now I'm going to use, or I'm going to invoke here just a constant. This is a proportionality constant that it can be, for example, adjusted with the different data plots that we can obtain from our experiment. And then what's important is that we put clearly here what is the proportionality between the growth rate and the biomass itself. Now, I would like to pay attention to the fact that here we have now obtained an interesting exponent, right? So if we remember what happened in exponential growth, I'm going to write it here just for comparison. In exponential growth, we normally had this type of ordinary differential equation, where the exponent was simply 1, and then we obtained exponential growth over time. Remember? Here, this is something that's a little bit different, but we can also solve for it given some initial conditions, no? Suppose that the inoculation was such that at time 0, we had some value of the biomass, namely B0. Can we now obtain the growth pattern or the total biomass over time for this system? And the answer is yes. Given this equation and this constant here, there is a parameter that needs to be adjusted, we can now solve this equation by variable separation, right? So here, notice I'm going from here to here. Basically, I'm going to take this in the denominator, right? And we are using classical variable separation. What I want to do next is I'm going to integrate from the initial condition to our goal here, function, which is how B grows over time. And here I'll have to do the same for initial time to time t. I'm going to use mute indices for t. Well, this integral is doable, right? We can solve this integral by, actually we can think of this by adding a 2 here and then adding a 2 here, and this is going to be the primitive of the following, right? And we are going to go from B0 to B of t, and we have to consider that we have added a 2 over here, so we add a 2 over here. Now we're going to solve for this, and then trivially on the right hand side we'll just have our constant and then times t, right? If we move down here, we are going to have, I'm going to put this 2 over the other side on the right hand side, okay? And now we move down there, we're going to have simply b of t to the power of 1/2, or if you want the square root of b of t, minus b naught to the power of 1/2, and that's at halves over here. And the exercise is pretty much done now. We see that we have that the square root of b of t, I'm going to write it in 2 different ways. I'm going to write this in 2 different ways, is a function that it's linear with t, and then it has some independent term here, which corresponds to the square root of the initial condition, right? So this could be thought of as the inoculation. In other words, we could actually square both sides of the equation now, and allow me to go up here, and we could say that for this specific system we had a growth of the total biomass that goes as follows. And importantly, I would like to remark that this has an exponent, which is 2, and on the next examples we will see that these exponents can change depending on the dimensionality and other structural patterns of the system that we are looking at. Okay? Well, let's move on with our next example, and let us now consider the figure that you also have in your paper, that it's actually extracted and adapted here from Goddard's. And the figure tells us something very interesting, right? So let us read a little bit into it. So here on the y-axis we have the number of cells of spheroid tumors of a particular type. But interestingly, this number of cells is actually scaled up, or it has an exponent here. It has a power of 1/3, or in other words, it's the cube root of the number of cells on the y-axis over time, right? And we can see that this time is of the order of days. The order of magnitude here that we are using is days. So, in other words, what we see here is the growth pattern of these spheroid tumors over time, but we have actually put it in a rather special way when we are plotting it by using this 1/3 exponent. The purpose of this exercise is to try to understand why are we using this, and is there some fundamental underlying pattern by which we can sort of guess why or what exponents we have to use in each case. So again, just as before, our first thing that we have to do here is we have to find what are the interesting variables, or the variables that we have to keep a look at, right? So first off, we want to explore how the number of cells is growing over time, right? So this is going to be simply our number of cells, so the total number of cells in the spheroid tumor. Okay, and we want to have some notion of what's the growth rate over time of this number of cells, right? So how is this system growing? Let's write here. Very simply, the growth rate of the number of cells. So the first hint for this, in order to tackle this problem, is to pay attention to the word spheroid, right? So these kind of tumors, they can be explored experimentally, and these are tumors that have a strong spherical symmetry. So again, if they have a strong spherical symmetry, and we, for example, pay attention to what's going to happen around the surface of this tumor, so if we, for example, take a zoom here, right? Very sketchy, what we see is that there's a frontier, there's a boundary for this tumor spheroid, right? Where the cells on the boundary are the ones that can keep growing. Just as the example that we've seen before. Whereas the cells on the inside of the tumor are now deprived of the nutrients that exist only on the boundary, and therefore they cannot grow any longer, right? So we have a very similar situation as before, only now instead of working with a Petri dish, we are actually working with something that it's sitting in 3 dimensions. Okay, so again, in this case, we can start looking for different proportionalities, and for example, we can start with the number of cells. In this system, the number of cells has to scale with the volume of the spheroid, right? So we can think of this volume as something that is pretty much spherical, therefore it has to scale with r to the 3rd power. Again, I'm using these constants here, but we can ignore them for the time being. I'm just putting them for completeness sake. And on the other hand, just as we argued over here, we are going to have something on the growth rate that it has to scale with the surface of this tumor, right? Instead of with the volume, because only the cells that are sitting on the surface can grow, then all the growth rate is going to be due to these precisely these cells. In other words, this has to scale with the surface of this spheroid tumor. Again, the surface is going to be basically scaling with a power of 2 of the radius. There's actually many ways that we can do this, but very simply we can see that out of this first relation, we know that the radius of this spheroid tumor is going to scale as n over 1/3. Notice that already here we are already seeing n over 1/3, which is the choice at which they started the problem with, the choice by which they started plotting this data. It's of course not random. Now we can plug this proportionality over here in order to obtain what I'm going to write over here, right? So basically from these considerations we can find that there's going to be this law of proportionality. Allow me to already introduce here a constant that can be obtained out of adjusting from the data. We're going to call this constant A without loss of generality. And notice that here I had r to the 2. Therefore, if I'm going to plug this relation over here, I'm going to have something like n to the power of 2/3. So remember that in the previous one we had a very similar equation, right? Where we had we were working with biomass before, so we had the biomass and it was proportional to the biomass over 1/2. This is not the same law. It's definitely something different, precisely because the exponent is different. Yet again, it's different from our simple linear growth models or exponential growth behavior that we have encountered previously in our previous lectures. But again, we can solve for this system and we can try to see what kind of patterns emerge from this, right? So suppose that we have some initial conditions, so that's the initial in the initial number of cells for this spheroid tumor, right? And we are going to call it N0. And from here, we can use variable separation, again, to find that we have to solve this simple differential equation. Okay, so here I've just separated variables, and next I'm going to integrate out. We're going to go from N0 to N of t, and here we're going to go from 0 to t accordingly, and then I'm going to use mute indices. So again, here we have an exponent that it's down there. We can solve this, as a matter of fact, by multiplying by 3 up and down. I'm going to do this next, so I'm going to find, so if I multiply this by 3 and also this by 3, here it looks like I'm doing nothing, okay, but as a matter of fact, I'm finding the primitive of this to be exactly n to the power of 1/3. So here we're going to have to solve this between n0 and the number of cells over time, which is our goal, and this is going to be proportional to this constant and times t. Then let's move down here for a second, right? So in order to keep going, we can put these 3 on the other side of the equation, on the right-hand side, right? And then very, very quickly, we can see that n over time to the power of 1/3 is actually a 3/3 plus n0 to the power of 1/3. And this relation here is very suggestive of something that we have already seen, right? Notice that here we naturally have obtained the choice of data plot that we had in the picture right there on the left-hand side of the border. And if we take this equation seriously, what we see is that the number of cells to the power of 1/2, or in other words, the cube root of the number of cells, is actually a linear function of t, right? It's a linear function of t. We could rewrite this expression up here by taking powers of 3 in both sides, and then that'll give rise to this. Now, this is not what it's plotted on the left side of the border, because now we have raised this to the power of 3. But this allows me to make a comparison to the exercise that we had before, right? Remember from before, we were working with bacteria, right? So we were using biomass or number of bacteria, wherever you prefer. And we had a similar relation here. This is going to be a different constant, obviously. So here we are abusing notation a little bit. But here, instead of this exponent 3, we had an exponent 2, right? I want to also notice that if we take asymptotic behavior, namely if we look at long time behavior, what we're seeing is that in these spheroid tumors, what we find is that the number of cells is going to scale like t to the power of 3, whereas for the bacteria system that on a Petri dish that we looked before, this scaled like 2, right? Notice that very importantly, the dimensionality of this system was 3, and that actually it's in accordance with how this system is growing, right? Whereas in the bacterial dish, in the Petri dish for bacteria, the dimensionality of the system was 2, and that's what occurs over here. And now we're going to do something, a bit of a generalization of how this dimensionality actually can break down somewhat, okay? So let's move on. Well, up until now, we have observed 2 different systems. One was growing in 2 dimensions. Remember, this was the bacteria strain growing in a Petri dish. The other system was a tumor system, tumor-like system, that it was a spheroid tumor and it was growing in 3 dimensions, right? And we have encountered 2 patterns of growth that, asymptotically speaking, or in long times, the first one, the 2-dimensional one, scaled like t to the power of 2, and actually this related strongly with this dimensionality over here. And then we had spheroid tumors that scaled like t to the power of 3, and it obviously had this connection with this being a three-dimensional system. But 3 dimensions is actually all we have, right? At least in biology. Can we actually move beyond this? Can we find systems that grow faster than this with all the given constraints and disregarding for now exponential growth? And the answer is yes. We have to keep in mind that biology is an evolutionary process, and in this evolutionary process there are multiple different innovations that can occur, and they will reshape the way that not only information but also energy is processed, right? And without moving farther from the realm of tumor systems, we can find tumor systems that grow in a very similar fashion from what it looks like in this plot from the example before, but very importantly, notice that here I wrote a different exponent. In this case, I wrote a general exponent, nu, okay? And now we're going to give some explanations for why this nu could be more succinctly described as something of the type 1/4 as in comparison to what we had before, which was 1/3. Remember, that's what gave rise to this 3 exponent here, and yet we can find tumor systems that by growing in a particular way that I'm going to explain now, they have this specific exponent. So first off, let's try to think what kind of equation can give rise to this exponent. We don't have to go very far. We have already seen the equations that are governing or are behind this sort of behavior, right? So in general, all the time what we had was something of this type, right? So we had the rate of growth of the number of cells that were found to be in these specific systems, in this case, in these tumors, was proportional. We're going to use some general proportionality constant here, to the number of cells to some power alpha. Okay. And now I'm going to mention something that is going to be largely explained in a seminar, but not in this lecture. But this exponent alpha for a large number of systems, specifically vascular systems with vascular capacity, this alpha here was shown many decades ago to be actually 3/4, but it wasn't until recently, until roughly the early 2000s, that this was explicitly explained by the use of fractal geometry in these vascularized systems, right? But for now, let's just pretend that we have such a law, and then we want to integrate this in general, which is going to be a good exercise, and we're going to find a relation between this and mu in general. So again, just as before, I have to integrate this by separation of variables, okay? So in this case, I'm going to have this very simple relation, and we are going to suppose that n at 0 is n naught, and therefore I can integrate this out, okay? And here use mute indices, and very simply this gives rise to the following solution, which I'm going to write down here. In this case, we'll have n to the power of 1 minus alpha divided by 1 minus alpha, and that's going to go from n naught to n over t. Here on the right hand side, again, as usual, we'll have just time like this. And I have to make an important notice here, which is the fact that alpha, in order for this to be true, alpha has to be different from 1. But as I have already explained, in fact, what we find in these systems is that alpha is close to 3/4. So using the fact that alpha is not going to be 1, we can easily derive this expression over here. Okay? Now it's a matter of taking factors out, etc. But very easily we can see that we are going to have n to the 1 minus alpha of t, right? It's equal to 1 minus alpha times a times t, all right? Plus n naught to the 1 minus alpha. Sure. And now we finally have an expression that kind of is similar to what we had before. And if we take long time behavior, so I'm going to go up here now. If we take asymptotic time, so for t sufficiently large, I see that n of t is simply proportional to t to the power of 1 over 1 minus alpha. Okay, so let's talk about a little bit more about the kind of tumors that can show or can display this specific behavior, right? So notice that if this is our relation, basically we could invert this again, we could inverse this and take n to the power of 1 minus alpha is proportional to t, and therefore our mu that we had right here on our data plot actually corresponds to 1 minus alpha. For these specific tumor types, what we have is some biological processes that stem out of the evolution of the whole historical evolution of the biological system. For example, angiogenesis or ruggedness behavior on the surface that allows for infiltration of nutrients into the system, and that transcends the dimensionality of these tumors. And in fact, for what West, Brown, and Enquist showed, alpha is going to be 3/4, which means that nu is going to be 1/4, right? So if we now plug in these values for what we had here, we can see that these specific tumors, instead of growing like t to the power of 3, actually they grow as t to the power of 4, which is going one extra dimension. If you think about it, it's like going one extra dimension beyond 3 dimensions. Obviously, this is not that's not to say that these tumors are growing at the 4th dimension, not at all. It's just that by utilizing this innovation from evolution, namely angiogenesis or fractal surfaces, they allow themselves to grow at a larger rate, or if you want, with a higher exponent over time, right? So this is one of the exploitations that tumors can acquire, and they make them, in this case, more aggressive, okay? I want to notice then that these specific exponents that we have been using, they are related, okay? They have a relation to the fractal dimension that's often used with this notation of the different systems that are on top of the tumor, namely angiogenesis or other fractal behavior, for example, the ruggedness of the surface, okay? Finally, and to finish with this session, let's go back to the very beginning, right? So we have spoken and we have gone beyond exponential growth, and we have used, in this case, a simple 2-dimensional system, another system that relates to tumors, namely the spherical ones that we explained in this case. We have even explored for the first time what are the consequences of extra structure on biological systems, and in this case, these fractal structures stemming from specific types of tumors. But are there other tumoral systems, for example, that can grow even faster than this? And for example, can I ask, are there systems like tumor type systems that grow, for example, exponentially, which we know these are, by definition, exponential growth is always going to overcome any polynomial type growth? The answer is yes, and I want you to ponder and ask yourselves what kind of cancer systems can grow in an exponential manner.